Hello everyone, this is Xiaohu from Duke University. Today I'm going to present some new results for massive parallel joins. This line of work has been motivated by the rapid development of massive parallel systems such as MapReduce and Spark. Join evaluation as one of the central problems in database theory has received much more attention. So this paper is a continuation of previous work on how to evaluate join queries efficiently in today's massive parallel systems. In today's talk, I will first give some background knowledge and then show the main results from two aspects: new upper bound for acyclic joins and the new lower bound for cyclic joins. At last, I will give a conjecture on this problem and conclude with a few interesting open questions. Let's start with the MPC model. There are P servers in a complete network. Initially, data is distributed across all servers. Computation proceeds in rounds. In each round, servers exchange data first and then perform local computation. Algorithms in this model are first measured by the number of rounds and then the load, which is the maximum size of data received by any server in any round. As global synchronization is very expensive, we only consider algorithms running in a constant number of rounds. Then the question is, given a query, a distributed database, and P servers, how to design a constant round algorithm achieving the minimum load? Natural join defined over two tables is to find all combinations of tuples that are equal on their common attributes. When there is a single value in the join attribute, it just degenerates to the Cartesian product. Evaluating a multi-way join is equivalent to the pattern matching problem in instance hypergraph, which uses the vertex to represent the values and the hyperedges to represent the tuples. We studied the data complexity of this problem, which assumes the query has constant size and use data-dependent quantities, such as input size for complexity measurement. In the RAM model, there is a unified worst-case optimal algorithm for all joins, which has been motivated by the AGM bound. AGM bound says that the maximum join size is bounded by n to the power of rho star. Rho star is the optimal fractional edge covering number of the join query. This bound is also tied with a matching instance. However, join evaluation in the MPC model is quite different from the RAM model. Previously, the target of the multi-round worst-case optimal algorithm was believed to be n over p to the power of 1 over rho star. The observation is that each server can generate at most L to the power of rho star join result in a single round, which is also implied by the AGM bound. Then P servers can produce so many join results in a constant number of rounds. As each join result must be emitted by at least one server, setting this quantity greater than the AGM bound will generate such a lower bound. So far, this lower bound has been achieved on the LW join and the binary relational join, where each relation contains at most two attributes. However, whether this bound can be achieved for arbitrary joins or even just acyclic joins is still open. So in this work, we make efforts towards answering a fundamental question. Is there a unified worst-case optimal algorithm for massive parallel joins? Our first result is the worst-case optimal algorithm for acyclic joins matching the edge covering dependent lower bound. Then we turn to cyclic joins. Surprisingly, we found that n over p to the power of 1 over rho star is not necessarily a correct target. We prove a higher lower bound in terms of the edge packing number for some degree 2 joins, where each attribute appears in at most two relations. This result also rules out the possibility of achieving a unified worst-case optimal join algorithm in terms of the edge covering number. Next, let's focus on the upper bound for acyclic joins. A join query is acyclic if we can put its relations into a join tree satisfying the attribute connectivity property. It can be easily proved that an acyclic join always has an integral solution for the optimal fractional edge covering, and our algorithm is exactly built on this observation. Given a join tree for an acyclic join, the idea is to break the join tree at every internal node in the edge cover and obtain a set of twig joins. Twig join has been identified as a special case of a cyclic join, which has a join tree whose leaves form an optimal edge cover. Intuitively, we will compute the original join by computing the Cartesian product of those derived twig joins. But how to compute them in order without repeatedly involving a relation multiple times requires some more effort, and the answer can be found in our full paper. Next, let's focus on how to tackle a twig join efficiently. We still resort to the heavy light decomposition strategy, but the key idea is to decompose the join instance from a single attribute in an aggressive way. We first choose an attribute that does not appear in the root, but in the unique child of this root, say attribute X. Let Y be the leaf node containing X. We identify a value in attribute X as heavy if it appears in more than L tuples in any single relation lying on the path from C to Y, and light otherwise. The value of L is essentially our target of the optimal node, which can be computed explicitly. Each heavy value derives a residual join by equivalently removing attribute X from all relations, which is still a valid twig join and can be handled recursively. For the light values in attribute X, we put them into groups such that each group has degree of at most L in each relation on this path. For the subquery derived by each light group, we just broadcast all relations on this path to all servers, and it's equivalent to solve the residual join by removing the relations on this path. Note that this is a set of disjoint twig joins, and each of them will be further recursively handled. But there are still many technical issues. How to combine the join result of a set of twig joins, and how to relate this recursive strategy with the optimal edge covering number. How to allocate servers to compute all subqueries in parallel. All these questions are answered in detail in our full paper. Finally, let's turn to the cyclic joins. This example has 5 relations, A, B, C, D, E, F, A, D, B, E, and C, F. It has edge covering number as 2 and edge packing number as 3. Previously, people didn't even have a full understanding of such a simple query. There's a gap on the existing best upper bound and the lower bound, which has been left as an open question. In this work, we show a new lower bound as n over p to the power of 1/3. This result also implies that the current single round algorithm is already optimal. Let me next show some intuition behind the proof. 2 basic arguments are used. First, each join result must be emitted by at least one server, and when a join result is emitted, all the participating tuples must reside on the same server. We first construct a hard instance, as shown on the left. Those numbers are the domain size of the attributes. Relations DEF, AD, BE, and CF are Cartesian products with exactly n tuples. Relation ABC is probabilistically constructed with n tuples in expectation. This instance also has n-squared join result in expectation. We next show that each server cannot achieve high efficiency in emitting the join result, no matter which combinations of input tuples it loads into local memory. More specifically, we bound the maximum number of join results one server can produce in a single round with 2 times L cubic over n. After that, applying the counting argument to this instance will give us this lower bound. At last, let's have a brief discussion on the existing result on worst-case optimal join algorithms. We know that this worst-case complexity is related to the edge covering number for acyclic joins, binary relation joins, and LW join, and related to edge packing number for some degree 2 joins. However, there is no clear distinction on the relative ordering between edge covering and edge packing number. A natural question is, cover or pack? Which one is the correct quantity capturing the hardness of the worst-case optimal joint evaluation? To clarify this question, we introduce the notion of reduced join. A reduced procedure is to remove a relation if it is fully contained by another relation. We can repeatedly apply this procedure until no more relation can be removed. From the upper bound side, a joint query can be reduced with linear load. So the hardness of joint evaluation comes from the reduced joint. Now we can draw some distinctions. On one hand, edge packing number smaller than the covering number holds for the reduced Berger cyclic joints and the reduced binary relation joints. It's also conjectured to hold on any reduced alpha cyclic joint, but the proof has not been published. On the other hand, edge covering number smaller than packing holds for the reduced degree 2 joints. Based on these observations, we conjecture that the worst-case complexity is related to the max of edge covering and edge packing number of the reduced joint. But this problem in general is still open. We have more questions to be further explored. For example, can we have a better algorithm for high-arity cyclic joints? And can we prove any lower bound beyond the degree 2 joints? Moreover, how to implement these algorithms in practical systems, such as Spark and Flink? And we need more efforts to bridge the gap between the theory and the practice in the future. Thank you for your listening.